Okay, so today I'll be presenting our project, Distilled Feature Fields Enable Few-Shot Language Guided Manipulation. And this is work with a great team of collaborators, and we published this at Coral 2023 this year. So the main motivation behind our project is how can we get robots to generalize? So let's ground this a bit more and talk about what we really mean by generalization. So how many products, or SKUs, which are stock keeping units, do you think a company such as Amazon has in its warehouses? Well, if you ask online, the number you'll get is around 12 million products. But that's just only Amazon's own products that they sell, not taking into account all of the 1 million products from the third-party sellers. So if we consider both the products Amazon sells and the products sold by the third-party sellers, there's in fact over 350 million unique SKUs or SKUs. So really, this number is very large. It really tells you the scale that these companies such as Amazon operate at. And really, this necessitates automation. And indeed, if we look at the logistics chain of Amazon, you'll see a lot of automation in place, such as conveyor belts moving boxes and totes around, and also robots picking and placing packages. But if you look at this a bit closer and dive a bit deeper, what you'll see is that humans still play a big role in the system. And on the video on the right, what you're seeing is a worker who's called a picker, and their job is to basically read an order manifest and then figure out which product the shelf is in, and then reach in and fetch the product and place it into a bin. And as you can imagine, this task is very cognitively expensive, and it's very difficult for a robot to be able to achieve, both in the perception and the control aspect. And in fact, this human would take over 400 years just to go through all of the 350 million products that Amazon has. So what we can say that's almost certain is that the worker is going to come across objects that they've never seen before on a day-to-day basis. Yet they're still able to understand and identify what item is what with a near 100% success rate. So the question we want to ask is how can we build robots towards this level of applications and this level of generalization? And more importantly, we care about open-ended generalization. And that is generalization to objects and concepts that were never seen before during training, much like how we as humans might generalize. So let's ground this in a robot tabletop manipulation environment. So here you can see a video of myself setting up a tabletop with a bunch of objects. And I'll just note that I picked these objects pretty randomly around the lab. They were not very cherry-picked at all. But what we want from open-ended generalization is the ability to grasp or pick and place any of these objects without previously having seen them in the past. So for example, I might ask the robot to pick up the Baymax object. And Baymax is this robot character from the Disney movie Big Hero 6. And we'd like the robot to be able to pick up Baymax even if it's never seen or been given a demonstration of how to do it in the past. And what we'll build towards during this talk is how can we go from a demonstration of grasping this caterpillar toy, which we might recognize from Dense Object Net's paper, to then grasping this Baymax. So this really open-ended level of generalization. And the focus of our work is understanding what's the scene representation that affords this level of generalization out of a box. So really for robots to operate in the world, they really need to understand what is where by looking. So basically, robots need to understand what's what in the scene and also where those things are in order to manipulate them. So we need an understanding of semantics to identify what objects are in the scene and what the different parts of an object could be based on text or other attributes. And we also need an understanding of geometry. So just understanding semantics is not sufficient. We need our robot to actually operate in a 3D environment. So ideally, we'd like to encode the geometry in 3D. And what we've seen recently is foundation models, specifically vision foundation models, trained on internet scale 2D images. They have a lot of common sense understanding and semantic understanding of a world. And at a high level, what these models do is you give it an image and you can feed it through the model to get these 2D feature maps, which have a very latent understanding. So they encode semantic understanding of a world in its latent features. However, these features alone are insufficient for us to get a grasp in 3D for the level of generalization that we may want. So we know we have these 2D foundation models that have very powerful semantic understanding, but they don't really represent 3D geometry. And on the other hand, we've seen the rise of neural radiance fields, or NeRFs, and more recently Gaussian splatting, and they're really the state-of-the-art representation for 3D geometry. So the question we want to ask is, can we marry these two representations together to provide both detailed geometry in the form of 3D and a fine-grained understanding of semantics by lifting these 2D features into a 3D representation? And this representation is called a 3D feature field. And it turned out that the graphics community has pioneered this 3D representation for things such as scene editing. So if you have a look at the video on the bottom right, what you'll see is that you can edit the video, say change the color of a flower by just using language. So it really shows you the ability of a scene representation, but what we want to see is how can we use feature fields for robotic manipulation tasks. And this is also what we call our method, F3RM or FIRM, and I'm going to talk about three of the components that make up this system. Firstly, how we can produce our 3D feature fields from the 2D foundation models in a robot manipulation setting. Secondly, how we can then use the representation to accomplish few-shot manipulation, so the robot's been given a few demonstrations. And finally, how we can add natural language for open text language-guided manipulation. And that truly unlocks the really open-ended generalization that we're looking for. So let's have a look at how we can produce the representation. So here's the scene you saw earlier, and here's the robot capturing 50 RGB images of a scene. So these are RGB images alone without any depth information. So we can capture these RGB images, and we assume we know the poses of the images. And then using that, you can construct a neural radiance field, or NeRF, of a scene. And I won't go too much into the details, but at a high level, what a NeRF does is basically train this neural field to render the training images. And from a photometric loss objective, you can basically learn the geometry and the 3D representation of a scene. So now we know we can go from 2D to 3D, but more importantly, besides the color pixel values, we also want to reconstruct these 2D visual features from these vision foundation models, such as Dino or Clip. So taking the same RGB images that the robot captured, we can feed them through our vision model to get these 2D feature maps. And now, since we know the geometry of a scene from the NeRF, we can basically train a feature field to render the feature maps instead of the RGB. And what this does is it basically lifts these 2D feature maps into a 3D representation. And what I'm showing here is basically a rendering of the 3D feature field, but showing you the principal components of the features, in this case, the Dino features. And what you'll see is basically the really clear difference in colors between the different objects. So it's showing you that there's some level of semantic difference in the feature space. So we know now how to produce this 3D representation. How can we use it for manipulation tasks? So we're going to provide human demonstrations to teach these robots how to pick up or place objects. So many manipulation tasks can be specified as a 6 degrees of freedom pose. So basically a rotation and a translation. And here I'm going to explain how we can represent these 6 DOF poses with our feature fields. So here's an example of a robot grasping this red mug. What we first do is sample a point cloud in the canonical frame of a gripper. And this point cloud basically rigidly transforms with a gripper. So as the gripper rotates or translates, all of these points translate and rotate with it as well. So given the demonstration, we can transform the points into the local coordinate frame of the grasp. And then if we have a feature field, we can then sample the features at each of these given points. And we call these red points the query points. Because the feature field is a field, we can query it by an XYZ coordinate to get the feature at that given location. We can then concatenate it into a single embedding, which represents our demo or our pose in this case. And you can see for the mug, we're basically trying to encode both information about the free space around the handle, the handle itself, and also parts on the body of a mug. So we know how to represent poses now. So how can we generalize to new scenes? So this is in a few-shot manipulation setting, and you can see on the left, we have a novel scene with this pink mug with this funny-looking handle shape. So we basically do test time optimization to maximize the similarity to a set of demonstrations. In this case, only 2 demonstrations. And what we're doing is we're trying to find the 6 degrees of freedom pose over the entire scene shown on the left that has the highest similarity to the demo embeddings. And if we run this on the scene, you see we can recover these top 10 graphs for the pink mug on the right. And then once you have those poses, you can then use a motion planner to find and execute them on the robot. So we've looked at how we can do few-shot manipulation, but how can we unlock open-ended manipulation via language? And we're going to achieve that by using clip feature fields. And clip, for those of you who are unaware, is basically a vision language model that's been trained on hundreds of millions of image and text pairs. And basically, you can give it an image to get features and also give it text to get features. And these features all live in this shared feature space. So let's consider asking the robot to pick up the bowl. And what you'll see is our pipeline consists of 2 stages. In the first stage, we can use language to retrieve the relevant demonstrations across a set of grasping priors. So we can extract the text features from clip for our language query, and then compare it to the query point features from our demos, since they live in this shared feature space. So in this case, there's a demonstration of grasping this caterpillar toy, but we assume we have a small set of demonstrations upon which we can repeat this computation of a similarity. And then what we can do is we can simply take the demonstration that has the highest similarity to the text query. So inherently what this is doing is trying to find the demonstration that best matches what the user asks for. And for picking up the bowl, it turns out that the demonstration we select is the demonstration for grasping this mug by the lip. And if you think about it a bit, it's pretty obvious to us that that would be a valid strategy compared to grasping a screwdriver or this caterpillar toy. So at least we know in the feature space, there's some level of semantic understanding here. So now given this demo we've just retrieved, we can then perform test time language-guided pose optimization. And here, in addition to just maximizing the similarity with the demonstration we retrieved, we also maximize the similarity with a text feature. So we weight the text features with the features from the demonstration. And what this does is it allows us to focus on the object the user specified in their query, but also use the local geometric and semantic features that we need, which is encoded in the demonstration. So we can run this optimization again over this entire scene. And as you see on the right, we can recover these grasps for the bowl. And this is despite the fact the robot's never seen how to grasp a bowl before. The closest thing, as you see, is how to grasp a mug by its lip. And the cool part is, even though we've retrieved a demonstration for grasping mugs, we can also ignore the mugs that are in the scene. And this is by basically using language guidance to weigh the optimization towards the object the user cares about. So we've looked at few-shot manipulation and language-guided manipulation. So now I'm going to show you some results on the real robot. So here's the scene you saw earlier with the robot scanning a series of RGB images. What we do is we first train the nerf and then distill our clip features. So here's a rendering of the nerf. And what you'll see is we're able to capture really precise geometric details, like the transparent mug and its handle, and also handle the reflective objects such as the metal jug. And these are things that an RGBD sensor, such as a RealSense, could struggle with quite a bit. But in addition to the nerf, we have the feature field as well. And here we show the PCA of the clip feature field. And what you observe is the objects have different representations in the feature space, which correspond to their different shades of colors. So throughout this project, all the results I've shown are using only 10 demonstrations. And these demonstrations are only across 4 object categories, which include the mugs that you saw earlier, screwdrivers, this one instance of a caterpillar toy, and also placing this cup onto the rack. And what we're really trying to explore and push is what level and what sort of forms of generalization we can get from feature fields given just this very small set of demonstrations. So the modes of generalization we would like is, firstly, if we can generalize to novel object categories. So that's categories that we haven't seen in our demonstrations, such as going from the mug to the bowl that you saw earlier, and also using language to query objects based on their appearances. So you can imagine having multiple instances of the same object type, but we want to see if we can use language to disambiguate them. And finally, specifying objects by their physical properties, such as their material. So let's first have a look at novel object categories. So we're going to ask the robot to pick up Baymax, which was the example you saw earlier. So the robot's never seen Baymax or how to pick it up before. But if we look at the similarity heat map of Baymax, the text query, over the clip feature field, what you'll see is that we're able to very clearly distinguish what Baymax is as a concept from all of the other objects in the scene. We can retrieve a demo for grasping the caterpillar and transfer that grasping demonstration over to this new Baymax instance. And here's the execution for the bowl that you saw earlier, which was the out of distribution object category. And if we look at the clip feature field and look at the similarity heat map, you can see that it's very easily able to pick out the bowl from the other objects as well. And keep in mind, this is basically a novel object category, but since we know how to grasp mugs by their lips, we can transfer that to grasping bowls by their rim as well. So now let's try querying objects based on their appearances. So we're going to ask the robot to pick up the blue screwdriver. And if you have a look at the scene, there's both a blue and a red screwdriver at the bottom. But what the power of language gives you is the ability to distinguish the objects and basically bias towards what the user is actually asking for. So here's the similarity heat map in the clip feature field. And what you'll see is that we're able to basically see that the blue screwdriver has a higher similarity compared to the red one. And basically, since we're only removing objects from the scene, we can reuse the feature field over and over again. So since we have demonstrations for how to grasp screwdrivers, we can transfer that over to the blue screwdriver, but this blue screwdriver is very visually dissimilar. It's larger as well, and also has the different handle color too. So in addition to just the blue screwdriver, we can also handle the red screwdriver. And if we look at the feature similarity heat map, you can see that the red screwdriver has a higher similarity than the blue screwdriver, which intuitively makes sense. And we can similarly transfer those demonstrations for grasping screwdrivers over to this red one. Not sure why that video didn't play, but let's finally have a look at querying objects based on their physical properties, and in this case, specifically by their material. So let's ask the robot to pick up the transparent jug. And this is one of the cool demos, because if I were to ask you, where is the transparent jug in this scene, you might say you can't really spot it because it's quite hard to see. But let me show you where it is. And if we look at the similarity heat map, you can see that the transparent jug really instantly pops out from all of the other objects. So at least the clip features allow us to very easily understand using language what the transparent jug is from, say, the metal jug or the bowl in the scene. And we retrieve the demos for grasping the mug by its lip similarly and transfer this over to the transparent jug. And just note that all of these objects were previously unseen by the robot. They all look very visually dissimilar from the demonstrations or are from a completely different object category. And what we're really showing is that feature fields allow us to achieve open-ended generalization. Just given a really small set of demonstrations, in this case only 10 demonstrations across 4 object categories, we can generalize to both novel object categories and also specify objects by their appearances and their physical properties. But I think the real power is giving users the ability to query what they want via language at these various levels of semantic granularity. So for example, the user could query for what they want an extremely high level, such as just asking for a children's toy, to a very low level, such as the Baymax character from the Disney movie. So that sounds all great and all, but there's a lot of important limitations of feature fields in general to be aware of. First of all, we really require dense views of a scene in order to reconstruct it faithfully. So nerf methods in general require lots of viewpoints. In our case, we use 50 RGB images in the scene, and that just really isn't feasible to collect in an actual deployment scenario. Secondly, we also need optimization per scene. So we're training this new scene representation per scene, and we're not reusing knowledge that we might have gained. So all in all, just to acquire the images and then train the representation, it takes around 2 to 3 minutes. And that results in a very static representation, which limits you to very static manipulation tasks, such as just pick and place. So if you were to say knock over an object, you'll need to recollect the images and train the representation again. And also, we inherently inherit all of the behaviors of vision language models. And specifically, since we look at clip can behave like a bag of words, where basically it doesn't really understand the intent behind the user's query. So if I had to ask the robot to say, pick up the object that's not a banana, it's really likely to be the case that clip doesn't understand the negation of what not banana actually means, and it goes ahead and picks up the banana. So there's a lot of concurrent work on feature fields that was at Coral this year as well, and they all are slightly different in terms of the representation they use or the grasping strategy they have. So for example, there's Act3D. They use more explicit point cloud representations and then project features onto those point clouds. There's also things like Lerf2Go, which also use these clip feature fields, but they take an off-the-shelf GraspNet to predict grasps on the given objects, and they take a more approach to focus on part-level grasping. And I think more interestingly, there are works like GNFactor, and they use generalizable or few-shot nerfs. And what that means is basically you can pre-train a generalizable nerf to basically predict the nerf and feature field just given a few views. So that really reduces the requirement from having, say, 50 RGB images of a scene down to just 3 or 4 views. But what we're really seeing is feature fields are becoming a viable 3D scene representation for open-ended generalization. And they could be used downstream for more things such as policy learning or as one of the conditioning inputs to a diffusion policy, for example. And we've looked at a very simple scheme with test time optimization, but just given that, we're able to enable out-of-the-box generalization over object poses, appearances, and categories, and specifying objects using language, in the case where we're using clip. So thanks for listening. If you're interested in checking out our paper, you can check out our website. We've also released our code. You can try feature fields both on tabletop environments and also in larger scale, say office or multi-room settings. And yeah, thanks and happy to take any questions if there's